Good morning, guys. How are you today? I'm going to continue from where I stopped on Wednesday. Good morning once more. I said I'm going to continue from where I stopped on Wednesday. Remember, we're looking at the story about the development of atomic theory and structure. And I gave information about the work of the first four philosophers that documented their work. Those that saw the development of atomic theory as just concept. Those that did not do any experiment like you. Remember, there is a general say, or there is a general belief in this part of the world that when rains is falling, and at the same time you see sun shining, the belief is that lion is giving birth in the jungle without any experiment, and some of you believe in such things. So scientists always believe in carrying out experiments if they conceive any idea. So the idea about matter, the idea about atom was first conceived by Leucippus and Democritus, which was later pushed a little forward by Aristotle and others. I remember I told you Aristotle, in his own belief, also believed that matter consists of various combinations of four elements. According to Aristotle, fire is an element, earth is an element, air is an element, and water. But from our knowledge today, we know that they are not elements. But that was the belief then, that was the concept without any experiment. And I told you that Dalton revolutionized chemistry with his hypothesis. And he was able to put forward what we know today as atomic theory, which, if you look at the information, most of the information put forward by Dalton are still valid, even though some of them there has been in an improvement, but he gives the information he put forward then helped us in developing what we know today as modern atomic theory. Then I later moved from that era of no experiments to era of experiments. And I gave information about the work of Thomson, Millikan, Rutherford, and even Faraday. I remember electrolysis. So it was from his work about electrolysis that we got to know that inside an ion, we have smaller subparticles that are charged. And from there, we saw the work of uh, others as well, Rutherford, Thomson, and even those that gave information about isotopes. Remember, all these are the work of scientists that they did based on some of the available information. So today, we're going to move a step further to look at other models. So one of the models we'll be looking at is that of Bohr model of atom. And I thought I will slow down a bit, unlike the way I gave the information on Wednesday, because now we have information that probably exam will be starting in April. So if the exam will be starting in April, I can still have my full 3 hours lecture before passing the baton to another lecturer. So hopefully I will let you know if we can have another lecture before Monday, or to have my third lecture on Monday so that I can complete my part. We can decide on that. So we'll be looking at Bohr model of atom. It proposed a planetary model. So I want you should be able to differentiate. Go and find out what is Rutherford model of atom. Rutherford model of atom. Can you hear me? Can you still hear me? No, yes. Yes, thank you. Thank you. It's okay. It's okay. Save time. So we're going to be looking at Rutherford model of atom. Sorry, I'm trying to push the laptop to do. What is the problem now? Yeah, the laptop is not responding. So that's why. And if I log out now, to come in is going to be a problem. Sorry about that. Yes, sorry about that. I was about giving information that I want you to go and check uh, the difference between Rutherford and Bohr model of atom. You're going to see some of the difference. If you look at Rutherford's model, he was able to confirm that the bulk of the weight of the nucleus of the atom is in the nucleus, and that the nucleus is positively charged. That's Rutherford. And that electron, which is negatively charged, is revolving around. Is that the belief of Rutherford as well? And the Rutherford is that the belief of Bohr as well? And did Bohr add any other information to it? These are some of the things that we need to know. Please, you are not supposed to just type any nonsense. You are only supposed to put your name, your matric number. Look at this student now, Alagbala. Your matric number is not complete. Some writing nonsense, you are not supposed to, please. And I only want to see your matric number and your name. And those on YouTube, you are supposed to do that as well. Put your name and your matric number. That's the only way we can identify you when we decide to check the attendance list. So let's look at Bohr model of atom now. He proposed planetary model in 1913. You can see the difference now. Nucleus surrounded by orbiting electrons at different energy levels, different distance from the nucleus, and that electrons have definite orbits. There is no part in between. And he also proposed that electron can jump from one energy level to another. And so he was able to show how different atoms interact and why they interact. So he proposed that electrons move in parts at certain distances around the nucleus, and that electron can jump from one energy level to another. Bohr also suggested that electrons can only revolve in certain orbits and certain energy levels. The word quantized, that energies are quantized. Electron cannot just be at anywhere. They have a fixed place where they must be. That was what he proposed. You can see, if you look at that step, the steps are quantized. They can only have certain place where a person may stand at every point in time if you are descending or climbing a stair. So he said electrons are what? Quantized. And so they cannot just be anywhere. They have a fixed place where they can be found. But there are a lot of work in between Bohr model of atom and Schrödinger. And what they did is a long story, but I will just try to summarize. For the development to move from Bohr model of atom to Schrödinger to quantum model of atom, there were a lot of experiments done by many scientists, before we now have the model that we refer to as quantum model. For instance, in classical physics, part of what they believe is that when you have the nucleus like that, and you have an electron revolving around the nucleus, what they know then, the information according to classical physics, is that as the electron is revolving around, is losing energy. And at a time will come when it will lose all its energy and spiral into the nucleus. That was the belief of classical physics. But in order for them to be able to explain that that is not the case, that wasn't the case, or that is not the case, they looked at electron. They looked at properties of light. And they now use the information from the properties of light to look at properties of electrons. And so they look at electrons as particles, and also look at electrons as waves. So they look at the wave properties of electrons and also look at the particle properties of electrons. There were a lot of experiments that were done at that time before they now arrive at what we know today as modern atomic theory. The modern atomic theory is based on quantum theory. So, but I will not waste your time looking at all that. But if you need more information and you want to understand all this, then you need to go and look for further information in textbooks. I said last week, on Wednesday, I can find most of this information in any general chemistry textbook. So, Schrödinger and Heisenberg looked at the nature of electrons based on available information. Remember, in Bohr model, he was able to tell us that you can find an electron in a specific level, energy level. But in terms of when Schrodinger and others developed their own model, they said no, it's not always possible to know the exact position of an electron. Now, if you know the exact position, then you are not going to be able to know the speed at which that electron is moving. So electrons don't travel in specific paths, but in a general area. And you can only predict the probability of finding an electron. You cannot be so sure. That was what they proposed, that you can only predict the probability of finding an electron in a location. So in Bohr model of atom, they use orbits. In Bohr model of atom. In quantum model, we use orbitals. Remember I said earlier that we are looking at the development of how we write electronic configuration 2881 to what we know today as 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And so when you look at Bohr model of atom, you are using A. But by the time you look at this, you are making use of Schrodinger quantum model of atom. Oguyemi, please, I don't have much. I'm trying to see what I can do to push as many information as possible. Yes? What is the problem? Unmute yourself, please. Unmute yourself.
So I said, can you explain?
Can I?
Can you explain the difference between orbitals and orbits?
That's what I've just given now. In an
I didn't
orbit,
get it.
the probability of finding an electron, you can only talk about the probability of finding an electron in a specific energy level. But in an orbit, you are saying, yes, you are sure that you can find an electron in a particular location. But in quantum model, you are saying the probability of finding an electron is going to be very high at a particular time, at a particular location, but you are not too sure, except you have information about it. So they were able to push this information across to us. They both explain the nature of electrons using some of the information I said. You remember I said they started by looking at light. They look at properties of light. They now try to adopt that properties of light to now look at electrons. And they were able to look at electrons in terms of particles and also look at electrons in terms of wave. And so they look at wavy properties of electrons. And so it was the combination of the efforts of many scientists, Planck, many of them, even Bohr, that gave the model that we know today. So instead of looking at atomic structure in terms of specific location of finding an electron, they now look at electron cloud model. So you can only predict the probability of finding an electron in a location. You cannot predict the exact place where an electron will be found. And you can see, looking at that now, you see that electron cloud, unlike the information given earlier that electron is going to be there, or the electron is going to be in that shell. You can only talk about the probability of finding an electron. So he took Schrodinger, that model of a Bohr. So he used a mathematical equation to describe the likelihood of finding an electron. And that is what we know today as the quantum mechanical model. That the exact path of electron cannot be predicted. But in Bohr model, he told us that yes, you can predict the exact path, location of an electron. But in modern quantum model, you cannot be so sure. You can see the region that is referred to as the electron cloud is an area where electron can likely be found. Then, in addition to the work of Schrodinger and others, some other people also discover, some other scientists also discover other sub-articles in the nucleus, and that they observe that neutrons have no electrical charge. Remember, they've been able to identify proton, and that most of the mass of the atom is in the nucleus. And now they've observed that the proton is positively charged. That was the work of Thomson and the rest. And they were also able to, that electron is negatively charged, according to Bohr and others, and that the electron is revolving around the nucleus. And now they've also been able to identify that neutron is also there and that it has no charge. All this you know. So according to Schrodinger, you cannot predict the exact, so you can only talk about the electron cloud, and you can see that there. Electron cloud. Chadwick is the one that discovered a neutron. Okay. So neutron has a mass nearly equal to the mass of a proton. So all these I'm going to send this note to you. So the current understanding that we know today is based on quantum mechanics, which looked at electron, the way the understanding, based on the understanding of properties of light, they also looked at electrons in an atom. In that, because when you talk of reactions taking place, it's about the movement of electrons. And that's why it is important to study the properties of electron. And that was why they were able to study the properties of electrons, and from there they were able to understand a lot of things about the atomic theory that was earlier proposed, and they were able to now understand the structure of atomic the structures of atoms. We now know that the idea that we have electrons revolving around is still valid, but that according to classical physics, as the electron is revolving, it is not losing energy. And as a result, consequently, it will not spiral into the nucleus. But it's only because we understand the properties of light and that we understand the properties of now electron that we now know that the electron, as it's moving around the nucleus, it is not losing energy. So that idea differentiates quantum mechanical model from Bohr model of atom. And you can see the model sees the electron not as individual particles, but as behaving like a cloud. The electron can be anywhere in a certain energy level. Unlike Bohr model, quantum model does not define the exact path of an electron, but rather predict the likely position where an electron can be found. Something like this. You can see that electron there revolving around. You started again, oh. So you have this modern atomic theory now. With the information we have now, we now know that inside an atom, we have smaller particles, which disproved the information given to us earlier by doubting that atom is the smallest indivisible particle. So we now know that in an atom, based on the story that I've highlighted, and that based on the experiment that were done by many scientists, we now know that in an atom, you have electron, you have protons, you have neutron, and that electron is negatively charged, proton is positively charged. So we have all this information already. I don't think we need to waste time on this again. So this information that we have there will also enable us to do little calculation, what you know from your O level, how to calculate mass number, proton number, and the rest like that. So we expect you to understand all this. The type of atom is determined by the number of protons it has. and the atomic number. So if they tell you the atomic number of an element is 15, atomic number, then you know the proton number is also going to be 15. And the electron number is also going to be 15 because it's an atom, it's neutral. The only time that the number of proton and electron will not be the same is when you have an ion. At that time, maybe the atom will have given, the element will have given out an electron, or will have taken electron or electrons. So all these are what you know. I will not waste time on this. The type of atom is this repeating. The sum of the number of protons and neutrons, you know all this. Mass number. Mass number is equals to proton plus neutron. All these are what you know. So the wave nature of electron, which I've discussed briefly earlier, Louis de Broglie postulated that if light can act as a particle, then particle can have wave properties. Remember I said they looked at light. So it is the understanding of light that now made it possible for us to understand the electron and to understand the structure of atoms that we have today. So he was able to put some equations together, or sorry, he was able to give us this equation that we use in calculating the properties, the wavy properties of electron. And from there, Heisenberg developed uncertainty principle, that it is not possible for you to determine the speed or the position at the same time. If you know the speed of an electron, then you cannot know the position. If you know the position, you cannot know the speed. And you can see that is where this probability, the uncertainty principle, came in. And since then, we've been able to use that, their idea, to explain a lot of properties that were not possible to explain using Bohr model of atom. So the quantum model is more advanced than the Bohr model or Rutherford model. Rutherford model, Bohr model is more advanced than Rutherford model. But by the time we now develop using a lot of experiments put together by many scientists, then we now know that the quantum model is more advanced than that of the Bohr model. And with that, we've been able to understand, like for instance, when you look at Bohr model, it was based on just n, which is the principal quantum number. But by the time we now looked at the model that we are looking at now, we now move from using just the principal quantum number to n, l, m, l, and ms, which has now enabled us to understand how to write electronic configuration. And that is what we're trying to do here. To understand the structure, now with the information that I've pushed across to you, we now know that atom is no longer the smallest indivisible particle as put forward by Dalton. We now know that inside an electron, we have 3 smaller particles. And we've been able to establish that the 3 smaller particles, one of them is negatively charged, which is an electron. One of them is positively charged, which is proton, and one of them has no charge. We've also been able to establish that, okay, the method, the information put forward by Bohr, that when electron is revolving around, it's losing electron based on classical physics, is no longer true. The electron is not, as it's revolving around, is not losing any energy. Consequently, it can maintain its speed around the nucleus. So all these are information put together. It's a long story. And like I said, all I've given you is just the abridged form of this history. It's not possible for me to give all the details, and you may not even find all the details in one textbook. So that's why we always combine a lot of textbooks when we want to put our information together. You can see as matter gets smaller, approaching the size, that's when you look at this, the Broglie's or the uncertainty principle, and if you combine it, you see that as it gets smaller, approaching the size of an electron, our measuring device interacts with matter and affect our measurements. It's very difficult so we can only determine the probability of the location or the momentum of the electron. We cannot do the two at the same time. So Schrödinger used some mathematical equations to look at that wave property of electrons. And so he introduced psi. We call it psi, Greek letter psi. And you can see that equation. This is Schrödinger equation. And you can see it is in 3 dimensions, unlike what you have in orbit, that in a Bohr model that is in 1 dimension. It's in 3 dimensions. And so with that, they were able to understand a lot of things about the wavy nature of electron. Note again, in that exam, I can decide to give you things like this equation, and ask you to get us some additional information from us, from the equation. How you can see dy dx, you remember your further maths. That's change in how psi changes in space. X direction, Y direction, Z direction. And we have the mass as that M there is mass, and the H is Planck constant, which has a value, Planck constant, which has a value. And you can see total quantized energy of the atomic system is the E, and V is potential energy. So all these are some of the things that you need to know about that equation put forward by Schrödinger. So psi squared gives the probability of finding an electron. And you can see in different directions now. So when you are looking at S orbital, according to this model, S orbital is spherical. So whichever direction you look at it, it will always be the same. But by the time you look at P, you can have P in X, Z. It can be P. That's why we talk of PX, PY, PZ that I'm going to look at later. So instead of using just principal quantum number in Bohr model, in this model now, we use quantum numbers. So a set of quantum numbers were introduced, and each of them describes a spatial distribution of electron density. So an orbital is described by a set of 4 quantum numbers, but I put 3 here, but there are 4 because by the time you see later, you're going to see that the 4th one was later added, but initially started with 3. So an orbital, unlike in Bohr model where we talk of orbit, in this model we talk of orbitals. So we use 4 quantum numbers to describe them. And the quantum numbers, you also look at them in 3 dimensions, X, Y, Z coordinates. So you have the symbols. So you have the principal quantum number. And the permitted numbers are n positive integers, 1, 2, 3 to infinity. Then you're looking at energy levels. Then you have the second one, which is the angular momentum. Integer starts from 0 to n minus 1. So if n is 1, for instance, L is going to be 0. You can see n minus 1. So it's going to be 1. Since n is 1, it's going to be 1 minus 1, which will be 0. And when it is 0, then it is s orbital. Can you see that? So when n is 2, for instance, now, the L value is going to be what? L value is going to be 0 and 1. And that will now mean you have s orbital and p orbital. Please, these are small letters, not capital letters. S, P. Then when n is 3, for instance, the L value is going to be what? Write your answer in the chat box. When n is 3, what's the L value going to be? Yeah, if you say 2, it's not correct. If you say 0, 1, 2, you are correct. Give yourself a big thumb. If you say 2, it's not correct. If you say 0, 1, 1, it's not correct. It's going to be, because remember, the L value, according to this information, is always from 0 to n minus 1. So if it's going to be from 0, the first one is going to be when n is 3. Then you substitute it into that. N is 3. When you substitute it to that, what do you get? 2. That's going to be 2. So, and it's starting from there. So it's going to be 0, 1, and 2. Then you have the ML value, which takes its information from where? From minus L to 0 to plus L. From minus L to 0 to plus L. For instance, if L is equals to 0, if L is equals to 0, then ML is also going to be 0. If L is 1, then ML, let me rub off the board so that you can see what I'm doing. So you can see the difference between Bohr model of atom, and through the class rep of, I don't know if they have any class rep, through the platform that I've created. I don't know if we can have another class before Monday. Just decide for me, those on Zoom and those on WhatsApp, if you can hear me clearly, decide if we can have a class. Since it's online, it's convenient for us to just meet, so that by next week, maybe another lecturer can come in and you can have another. But I'm also going to send today, after this class, I will put together the expected course outline. One of you sent a message, a WhatsApp message to me on Wednesday. I will send that course outline to all of you so that you can have a look at it and also prepare yourself. For the serious students, I know they will always read ahead of the lecturers, and so they will have information about what the lecturers will be talking about. So I said, if ML is 1, if L is 1, ML small l is going to be -1, 0, +1. Okay? And that's why when we talk of if L is 1, what is the letter? Write it in your chat box. We have SPDF. So what's the letter going to be if L is 1? Look at the information here. If L is 1, what's the value going to be? Look at this information. I circled it now. That's where the information is. When L is 0, the shape is going to be S. When L is 1, the shape is P. When L is 2, the shape is D. When L is 3, the shape is F. Okay? So the ML will take its own value from L. And that's why you talk of it's going to be -1, 0 to +1. That is the value here. So, for instance, now, when L is 1, what is the value there? What's the shape? Thank you. P. And it's small p, not capital P, please. Small p. So it's P. Remember, by the time we look at how to write electronic configuration now, what you're going to see is that we have PX, PY, and PZ. They are small letters, please. PY, PX, and PZ. And we're going to look at rules. When we meet again, we're going to look at rules guiding them, guiding the filling of these orbitals. Already, we've moved from using orbit 2881 to using orbitals now based on modern atomic model or quantum atomic model. So please go and look at the story again. Look at the stories are not just there for storytelling sake alone. They are there for you to understand how the structure, the atomic structure that we have today, how we arrived at that structure that we have today. And so use that to now look at the way we write electronic configuration. So at your level now, with this information, and by the time we complete our lecture, whether today or Monday, whether before Monday or on Monday, it will be a big crime for you when I ask you to write electronic configuration to now give me 2881 as the way to write electronic configuration of any element. At your level now, I will expect you to be able to use 1s2, 2s2, and to be able to tell me which one of them will be diamagnetic in nature, which one will be paramagnetic. All these are some of the information that you can get when you use this modern model of atomic structure. Questions, relevant questions. So through the class reps, please let me know if we can still have agree. You don't have to come to that platform and start loading it with unnecessary information. Agree with your members and let's know if we can meet before Monday. Otherwise, if it's not possible, then we'll use Monday class. But I would have loved that another lecturer start next week so that they can have Monday to, yeah, the last one was later introduced. And that's that's the one we refer to as MS. It was later introduced, and that you will see that later when we look at just a student asked, I saw in the chat box, which textbook to use. I gave information earlier that any general chemistry textbook, and that it is always good to look for textbooks first. When you have information from a good textbook or from textbooks, then you can now decide to go online for additional information. But if you don't get your facts from textbooks, by the time you get to the internet, you will see a lot of information and some of them can confuse you. That's why you always need a textbook. Any general chemistry textbook will do the magic for you. General chemistry textbook. Okay? And so the student just asked now, how about the fourth one? Yes, the fourth one is MS. And it takes its value. Permitted value is plus half and minus half. We're going to tell you how to use that. For instance, if you have helium is number 2, atomic number of helium is 2. I just want to show you how to use that before we go. But we are going to see it by the time we try to complete my own part of the lecture before Monday or Monday. If you want to represent this as 1s for helium, and we said is 1s2, the way to write the configuration of this is to put one arrow up to show the first electron. And this will carry the MS value of this is plus half. Then you have another one that is looking down. The MS value of this is minus half. So that is looking at the magnetic properties of electrons. So we can discuss this when we meet again. In the absence of any question in the chat box and no hand up, I think we can call it a day so that, okay, there is a Oni from systems. What is your question, Oni?
Sir,
Oni, yes.
sir, can you come again about this MS and
About
this
what?
the MS you were talking
The
about right
MS
now?
is the fourth quantum number that is used to describe the electrons. Okay? And that it can only take 2 permitted values. It can take plus half and minus half, or minus half. Is that clear? And that when you want to represent them, say you are writing electronic configuration, too many hands up. The only way to represent them is when you see the arrow facing up, then you know is plus half. The MS value for that is plus half. And when you see your arrow facing down, the MS value for that is minus half. That's what I've said. Adoju Telego. Thank God I'm not one of them. Unmute yourself.
Good.
Yes.
Good morning, sir. So I wanted to ask that what is that permitted values?
Yes.
Permitted values on something like oxygen. What is the permitted values? Like I don't understand the permitted values.
That's what we're going to do next week. We're going to write the electronic configuration. For instance, by the time we meet next week, one will expect you to be, what's the atomic number of oxygen? Atomic number of oxygen is 8.
16.
Oxygen is not 16, it's 8. Atomic number.
8.
So the electronic configuration of that will now be 1s2, 2s2, 2p,
Okay.
2p what? 2p4.
6. 4.
2p4. Then with that now, we can now decide to represent it. But what we are going to emphasize next week again is why is, I want to take another color. Why is this first one not 1s3? Why is the second one not 2s1? So all these are some of the things we're going to learn next week, or if you are able to give me a time today. Adesanya, it's time. If you have another class, that's why I'm conscious of the fact that you're supposed to go for another class. But if you still have time, I'll be available. I'm available to answer questions. Yes, Adesanya.
Good morning, sir.
Morning.
So in the last class, you said
Yes.
John Dalton made the atomic theory in 1807.
Okay.
But in the textbooks I've been looking at,
Yes.
it was 1808 it was recorded as.
1808.
Yes, sir.
Yeah, well, we'll still, it depends on the counting. We're going to look at the one that is common, so that even if I'm going to ask a question like that, I will not put 1807 and 1808. I will cause that confusion. I will look at dates that will be far apart, so that at least you will still be able to pick something that is close to the answer. Does that answer your question?
Yes, sir.
Thank
Thank
you.
you, sir.
Yes. Abiodun Abi.
Hello, sir. Morning, sir.
Yes, morning.
Sir, I want to ask that can you give us another element for that MS? Another example.
Anyone, just any one of them. For instance, this oxygen that I just gave you now, if I want to represent this, and these are what we are doing next week. We're already doing it now. If I want to represent this, I will just put a square bracket here. That's for 1s. 2. I'll put another square bracket. That's for 2s2. And I will now put 3 brackets. And that's for 2p x, 2py, and 2pz. Then I can represent them. That's the permitted value. Then this will go this way, this will go this way again as well. By the time I get to this place, we have 4 of them here. What the permitted value, which I'm going to discuss, the rule guiding that, is that I must give all of them 1 1 first. Then 1 goes to any of the 3 now because they are of equal energy. Take Joseph, other Phillips. Phillips, unmute yourself. Guys, let's leave all questions again. Just let's leave it until we meet again because of time, so that you can go for other lectures. Thank you for your time, guys. See you when you're able to get, through WhatsApp. You can send message to me, but I don't want unnecessary messages. Thank you, guys. Bye-bye. Enjoy the rest of the day. I will log out everybody now.